So in this session, let us learn about two different types of differentials, namely the exact and inexact differentials. So let's consider a function, say z, which is a function of x and y. So let me write z equal to z of xy, and let it be a continuous function of x and y. Now I can take the differential of z. So I'm writing dz. dz equal to, I can take dou z by dou x, dou z by dou x, keeping y as a constant, into dx, you know this differential rule, plus second term will be dou z by dou y, keeping x as a constant, times dy. So let me write this one as equal to some m dx plus n dy. We call this equation number 1, where you can see that what is m and what is n, where m stands for dou z by dou x at constant y. It's understood, at constant y. And n is equal to dou z by dou y at constant x, where this z, m, n all are functions of x and y. Now let me partially differentiate this m with respect to y. Partially differentiating m with respect to y. You know, m is already partially differentiated with respect to x. Now let me partially differentiate with respect to y. So what I will get? I will get dou m. You can write dou m with respect to dou y, dou m with respect to dou. So when I am differentiating with respect to y, I have to keep x as a constant. So what would be that equal to? It would be equal to dou by dou y of what is m? That is dou z by dou x. Dou by dou y of dou z by dou x. So which I can write as equal to a second order partial derivative dou square z by dou y dou x. So let me call this equation number 2. In the same manner, you can partially differentiate n with respect to x. So what you'll be getting? You'll be getting dou n with respect to dou x. Dou n with respect to dou x. So what will be the result? You can predict it will be equal to dou by dou x of what is n? Dou z by dou y. Dou z by dou y from here. I have taken it, which can be written as a second order derivative dou square z by dou x dou y. So that is my third equation. You know, as per the basic property of partial derivatives, mixed second order derivative is independent of the order of differentiation, since the order of differentiation, I'm writing differentiation, is not significant or is not important. What I can write from equation 2 and 3. So equation 2 and 3 implies that dou m with respect to dou y, keeping x as a constant, is equal to dou n with respect to dou x, keeping y as a constant. So this is my equation number 4, where m is defined by this particular equation and n is defined by this particular equation. If this condition is satisfied, which condition? Equation number 4. So if equation 4 is satisfied, if equation 4 is satisfied by any function z which is defined initially, then dz is called, then dz, just defined by equation number 1 above, is called an exact differential. Exact differential. That is a mathematical definition of exact differential. We'll come to its physical meaning. This is our mathematical language that we are usually using. Now, what is the meaning of an exact differential? It's also known as a perfect differential. If you want, you can call it as a perfect differential. Perfect differential. Exact differential is otherwise known as a perfect differential also. So let's see what's the meaning of this exact differential. So let me just come to the meaning of exact differential, right? See, the meaning is that you can readily integrate such a differential. That means you can take, for example, suppose I am integrating this differential dz, say from one initial value to the final value, dz, integral dz from 1 to 2, then 1 is the first state and 2 is the second state. Then you can written as what? The final value of z, integrating dz should give you z at the final value minus z in the initial value, z2 minus z1. And what was z2 and z1 for us? Z was defined as a continuous function of x and y. So I can write this is nothing but meaning f of x2 comma y2 minus f of x1 y1. So you can see that if dz is an exact differential, then the integral of dz will depend only on the initial and final values of the variables x and y, and it is independent of the path. It is independent of the path. So means what you can say, integral dz depends on the initial and final values of x and y, or it is independent of the path followed. It is independent of the path followed. Hence suppose that the path is a cyclic one. If the path is cyclic, for a cyclic path, you know what's meaning cyclic path, a path which starts at a point and it comes back to the same point. For a cyclic path, you know the initial and final points will be the same. That is Z2 will be equal to Z1. Z2 will be equal to Z1. So in that case, what about the integral becoming? Therefore, I can represent the integral by putting a circle over the integral. You know that this is what is known as closed integral. We call as closed line integral if needed, because the boundaries are 2 points. It is a line integral here. So closed integral of dz. Closed integral of dz means integral of dz over a closed cyclic path. Okay, that will be equal to, what is that? Z2 equal to Z1. Therefore, closed line integral of dz will be equal to Z2 minus Z1, which is equal to what? 0. So this particular equation also can be regarded as the test for verifying whether a given differential is exact or not. So if such a result you are able to get for a cyclic path, I can say dz is an exact differential. Dz is an exact or perfect differential. So this is the way in which you can conclude. If the integral of a differential between two arbitrary limits is path independent, or if the integral around a closed path is 0, then that differential is known as an exact differential. And whichever integral that does not obey these relationships, means if cyclic integral of dz is not equal to 0, then that dz will be known as an inexact differential. So the physical meaning of this differential exact and inexact is that an exact differential can be readily integrated. So it can be integrated directly, whereas in order to integrate an inexact differential, you need to use some sort of an integrating factor, which is not giving you a ready integration. So we will be using this exact differential in thermodynamics to denote a type of thermodynamic function known as state functions. We will discuss about the state functions in the next video. So this is my pointer for this session, and exact differential corresponds to a state function in thermodynamics. Corresponds to a state function in thermodynamics. So in the next video we will discuss the difference between a state function and path functions. Thank you.